We are going to discuss theorem 3.2.3, which is completion of an inner product space. The statement is like this: for any inner product space X, there exists a Hilbert space H and an isomorphism A from X onto a dense subspace W subset of H. The space H is unique except for isomorphisms. This theorem is very similar to the older theorem 2.3.2, which we have already proved in case of a normed space and a Banach space. Okay, so this theorem states like this: if we have any inner product space X that is incomplete, then there exists a Hilbert space which is named as H and an isomorphism A from X onto W, which is a subset of H, and W is a dense subspace. The space H is also unique except for isomorphisms. So let us move into the proof of this particular theorem. I have just quoted the theorem 2.3.2, which we will be using to prove this theorem 3.2.3. So let's refer to the older theorem 2.3.2, which states that let X is equal to X and norm be a normed space, then there is a Banach space X cap and an isometry A from X onto a subspace W of X cap, which is dense in X cap, and the space X cap is unique except for isometries. So what we are given is an inner product space X which is not complete, and our aim is to find out a Hilbert space, a complete inner product space from X. Okay, so the aim is to prove every inner product space can be made into a Hilbert space, which is nothing but a complete inner product space. And as we already know, every inner product space on X defines a norm, and this norm is defined by norm of X is equal to square root of inner product of X comma X. Okay, so by applying the above stated theorem 2.3.2, we can say that for a normed space X, there exists a Banach space X cap and an isometry A from X onto a subspace W of X, which is dense in X cap, and the space X cap is unique except for isometries. So we are going to apply this particular theorem. We have an inner product space X which defines a norm which is given by norm of X is equal to square root of inner product of X comma X, and to apply the above stated theorem 2.3.2, since we have a norm X which is induced by the inner product X, we can directly use this particular 2.3.2 theorem and use it in our proof. Okay, so here we are going to take the Banach space named as H instead of X cap. Okay, so down the line sometimes you might see X cap or sometimes you might see H, where both refers to the same thing. H is equal to X cap is what I have named it throughout the proof over here. So X is an inner product space, which implies that X is a normed space. Okay, and there exists a Banach space H and an isometry A from H onto a subspace W subset of H, which is dense in H. So that is what we get by using the older theorem. So now we have got that H is a Banach space. What is a Banach space? Banach space is nothing but a complete normed space. But what we have to prove in this particular theorem is H is a Hilbert space, which is a complete inner product space. So right now we have got that H is a complete normed space. We also have to prove that it is an inner product space. Okay, so in order to prove that H is a Hilbert space, what we need to prove is H is an inner product space and H is also a vector space, because every inner product space is defined on a vector space. So first we will be proving it is a vector space, Then we'll be proving it is an inner product space, and then we will come to the final part of this proof. So first we are going to construct the Hilbert space H, which is named as X cap. Okay. So we take two Cauchy sequences, arbitrary Cauchy sequences in X, which is named as X sequence Xn and sequence Xn cap, and we are going to define an equivalence relation between Xn and Xn cap, which is denoted by sequence Xn equivalent to sequence Xn dash if inner product of xn dash tends to 0 as n tends to infinity. So we can also write the norm of this one, norm of xn minus xn dash also tends to 0 as n tends to infinity. Okay, so we are going to choose an element x which is a member of capital X, and let x cap be the set of all equivalence classes x, small x cap, y cap, etc. of Cauchy sequences thus obtained. Then x cap consists of all the Cauchy sequences that converges to x. Okay, the proof goes in a similar fashion as we have proved in 2.3.2. So we can always refer to the theorem 2.3.2 if we have any queries regarding the construction of this particular space H, which is equal to x cap, or the equivalence relation, the way we have defined the equivalence relation. And we are going to define an inner product. This particular Hilbert space is to deal with a complete inner product space. So we have to define an inner product on x cap by setting inner product of x cap y cap is equal to limit n tends to infinity, inner product of xn yn, which will be used down the line, where this sequence xn and sequence yn are the representatives of x cap which belongs to capital X cap and y cap which belongs to capital X cap respectively. Okay, so first we are going to prove that x cap is a vector space. X cap or H, some places I might have written x cap so that we can easily coordinate with 2.3.2 theorem, where in some cases I would have mentioned H also. Throughout this theorem, H and x cap, it means the one and the same. Okay, so in order to prove that x cap is a vector space, we have to prove the vector addition holds, scalar multiplication holds, the zero element exists, the inverse element exists, and so on. So first we are going to prove the vector addition. For that, let's take two elements x cap and y cap belonging to capital X cap. So since small x cap is a member of the capital X cap, we can say that associated with x cap there exists a sequence xn, and similarly associated with y cap there exists a sequence yn. Okay, so let us take z cap as the sum of x cap and y cap. So in order to prove that capital X cap is a vector space, we have to prove the vector addition. So which means that if you take any two elements of that particular space, we have to show that it is closed under addition. So we have to prove that x cap plus y cap, which is equal to z cap, also belongs to capital X cap in order to prove that vector addition holds in the space capital X cap. That is what I have written. To prove vector addition holds in capital X cap, we need only show that x cap plus y cap belongs to capital X cap, where x cap and y cap is a member of capital X cap. That is to show that z cap is a member of capital X cap. That is to show that there exists a sequence Zn, and Zn is equal to xn plus yn, and sequence Zn is a Cauchy sequence. Now we are going to prove that sequence Zn is a Cauchy sequence. So in order for us to prove that sequence Zn is a Cauchy sequence, we have to prove that norm of Zn minus Zm is less than epsilon, so that we will say that sequence Zn is a Cauchy sequence. So let's see what is norm of Zn minus Zm. We have taken Zn as xn plus yn. Okay, so norm of Zn minus Zm can be written as norm of xn plus yn minus xm plus ym. So we are going to regroup the members which is there inside this norm, so that xn minus xm becomes one quantity and yn minus ym becomes one quantity, okay, which is one and the same. So which is equal to norm of xn minus xm plus yn minus ym. By triangle inequality of the norm of inner product, we can say that which is always less than or equal to norm of xn minus xm plus norm of yn minus ym. And we have already stated that sequence xn and sequence xm or sequence yn are all Cauchy sequences. So each one of this is less than epsilon by 2. So we can write it is less than epsilon by 2 plus epsilon by 2 for all m and n greater than or equal to maximum of capital N1 comma capital N2. Okay. So which is equal to epsilon for all m and n greater than or equal to maximum of capital N1 comma capital N2. So we have got that norm of Zn minus Zm is less than epsilon for all m comma n greater than or equal to maximum of n1 n2, which means that sequence Zn is a Cauchy sequence. So we can write that Zn is equal to xn plus yn is Cauchy. So from this we can say that Z cap is equal to x cap plus y cap belongs to capital X cap. So vector addition holds in this particular case. Now we have to prove that our definition is independent of the choice of sequence xn and sequence yn. Okay. So what we have to prove is it doesn't depend on the arbitrary elements that we have chosen for this. So that is why we are going to take two sequences, sequence xn dash equivalent to sequence xn and sequence yn dash equivalent to sequence yn. What we have to prove is the new sequence Zn is equal to xn one second. Okay, that is to prove that the new sequence Zn is equal to xn plus yn is Zn dash is equal to xn dash plus yn dash is equivalent to Zn is equal to xn plus yn. This place has been omitted here. When I've taken the scanned copy, please write it down. Now by definition, sequence xn dash is equivalent to sequence xn implies the inner product of xn dash xn tends to 0 as n tends to infinity, from which we can also write that the norm of xn dash minus xn tends to 0 as n tends to infinity. So let's see what is the norm of Zn dash minus Zn. Norm of Zn dash minus Zn is equal to norm of xn dash plus yn dash minus of xn plus yn. Okay, we are just going to split it up. What is Zn dash? Zn dash is equal to xn dash plus yn dash and Zn is equal to xn plus yn. So this minus is common for both the terms. So just regrouping the members which are there inside the norm we get, which is equal to norm of xn dash minus xn plus yn dash minus yn. So by triangle inequality we can always say that this quantity is less than or equal to norm of xn dash minus xn plus norm of yn dash minus yn. Each of these quantities is less than epsilon by 2, so that we can write which is equal to epsilon by 2 plus epsilon by 2 for all n greater than or equal to capital K. So what we have got is, So what we have got is sequence Zn dash is equivalent to sequence Zn. That is, if sequence Zn is a Cauchy sequence, then the new representative sequence Zn dash is also Cauchy. That is, our definition is independent of the choice of representatives. Okay. So next we are going to prove the scalar multiplication property of a vector space. That is, if x cap belongs to capital X cap and alpha is any scalar, then we have to prove that the product of these alpha into x cap also belongs to capital X cap for us to prove that scalar multiplication property also holds for this space. Okay, so let's take this particular alpha into xn sequence alpha into xn as tn. Okay, so we are going to prove that sequence tn is Cauchy. Since we know that sequence xn is Cauchy, so we can write, see, norm of xn minus xm is less than epsilon by modulus of alpha for all m and n greater than or equal to capital K. We have some purpose why we have taken epsilon by modulus of alpha instead of epsilon or epsilon by 2, so that we will get a particular quantity towards the end. Okay, which we'll see coming forward. So norm of Tn minus Tm. Let's see what is norm of Tn minus Tm. It is equal to norm of alpha into xn. We have taken Tn as sequence alpha into xn. Okay, so Tn will be substituted by alpha into xn and Tm will be substituted by alpha into xm. So obviously we can take alpha outside, which can be written as norm of alpha into xn minus xm. So by the property of the norm, norm of alpha into x is equal to modulus of alpha into norm of x. So by using that property, we can write it is equal to modulus of alpha into norm of xn minus xm. So which is equal to modulus of alpha into, let's substitute what we have got here, norm of xn minus xm is less than epsilon by modulus of alpha. So when we substitute it, we get modulus of alpha into epsilon by modulus of alpha for all m and n greater than or equal to capital K. Obviously this modulus of alpha and modulus of alpha gets cancelled out, so we get the remaining part as epsilon, which is equal to epsilon for all m and n greater than or equal to capital K. That is, norm of Tn minus Tm is less than epsilon for all m and n greater than or equal to capital K, which is nothing but the definition of a Cauchy sequence. So from this we can say that sequence Tn is a Cauchy sequence, that is alpha into x cap belongs to capital X cap. Okay, so now we have to also prove that it is independent of the choices of sequences selected. That is, if sequence xn dash is equivalent to sequence xn, then we should prove that alpha into xn dash is equal to named as tn dash is equivalent to alpha into xn, which is equal to tn. That is, we take sequence xn dash and sequence xn to be equivalent, then we have to prove that the new sequence tn dash is equivalent to tn, where tn dash is named as alpha into xn dash and tn is named as alpha into xn. So let's see what is the norm of these two entities. So norm of tn dash minus tn is equal to, let's substitute the value of tn dash and tn from here. We get norm of alpha into xn dash minus alpha into xn. So alpha can be taken as a common value, which is equal to norm of alpha into xn dash minus xn. So by property of norm that we have stated earlier some time back, we can write it as modulus of alpha into norm of xn dash minus xn, which can be written as, which is equal to modulus of alpha into epsilon by modulus of alpha for all n greater than or equal to capital K by substituting the value of norm of xn dash minus xn what we have got earlier. Okay, so which is equal to epsilon for all n greater than or equal to capital K. So we have got sequence Tn dash is also equivalent to sequence Tn, which proves that it is independent of the choice selected. Okay, so next we have to prove that 0 is a part of, 0 cap is a part of x cap. Okay, so 0 cap belongs to x cap, consists of all the Cauchy sequences converging to 0, and let x cap belongs to capital X cap, which implies that minus x cap is all the Cauchy sequences of the form minus sequence xn, sequence minus xn. Okay, where xn belongs to capital X. We know that sequence xn belongs to x, right? So minus xn obviously, minus xn is definitely related to minus x cap. So also if x cap and y cap belongs to capital X cap, then we have already got vector addition holes, that is x cap plus y cap belongs to capital X cap, and alpha into x cap, which is scalar multiplication, it also belongs to capital X cap. So we have proved that capital X cap is a vector space. Okay, so the first part is done. Next we have to prove that capital X, inner product of x cap y cap is equal to limit n tends to infinity. Inner product of x and yn is an inner product. And this is very much required because we have to prove that capital X cap or H is actually an Hilbert space. Okay, so whatever we have defined earlier with respect to the inner product, we have to prove that it is actually an inner product. For this we have to prove all the properties that we have studied for inner product. Okay, so since sequence xn and yn belongs to capital X and capital X is an inner product space, we can say that inner product of x and yn is also an inner product for all n. Okay, which is very clear, it's evident. Now we have to prove that inner product x cap y cap is an inner product. We need only show that it satisfies the properties of an inner product. So let's take x cap, y cap and z cap, three elements to be members of capital X cap. So the first property of inner product space is we have to prove that inner product x cap plus y cap comma z cap is equal to inner product of x cap z cap plus inner product of y cap z cap. So let's take the LHS, inner product of x cap plus y cap comma z cap. So by our definition we can write it is equal to limit n tends to infinity inner product of xn plus yn comma zn by definition. Okay, which is equal to limit n tends to infinity. We know that xn, yn and zn are it forms an inner product, right? So inner product of xn plus yn comma zn can be written as inner product of xn zn plus inner product of yn zn. Okay, so if you apply limit n tends to infinity separately for each of these terms inside, we get limit n tends to infinity inner product of xn zn plus limit n tends to infinity inner product of yn zn. What is this? This is actually inner product of x cap z cap and this is actually inner product of y cap z cap. So we can write which is equal to inner product of x cap plus z cap plus inner product of y cap plus z cap. Okay, so the first property is proved. Next, inner product property 2 is if alpha is a scalar, then we have to prove that inner product of alpha x cap comma y cap is equal to alpha times inner product of x cap y cap. So inner product of alpha x cap comma y cap is equal to, by definition we can write it is equal to limit n tends to infinity inner product of alpha xn comma yn. So we know that this inner product exists. So what is this value? It can be written as alpha times inner product of x and yn, which is equal to alpha into limit n tends to infinity inner product of x and yn. This quantity is nothing but inner product of x cap y cap. So we can write which is equal to alpha into inner product of x cap y cap. So the second property of inner product space is also proved. Next is inner product property 3. That is to prove inner product of x cap y cap is equal to inner product of y cap x cap conjugate. Okay, so let's see what is inner product of x cap y cap. This is equal to limit n tends to infinity inner product of xn yn. Inner product of xn yn is already an inner product, so we can write it as inner product of yn xn conjugate. That is, we can write this is equal to limit n tends to infinity inner product of yn xn conjugate. Okay, so which is equal to limit n tends to infinity inner product of yn xn conjugate. this is nothing but inner product of y cap x cap conjugate. Okay, so the third property is also proved. The fourth property is we have to prove that inner product of x cap is greater than or equal to 0, and inner product of x cap is equal to 0 if and only if x cap is equal to 0. Now, inner product of x cap, this is equal to limit n tends to infinity inner product of x and yn, which is greater than or equal to 0. This implies inner product of x cap is greater than or equal to 0. Okay, so here you can write actually xn instead of yn. Okay, I've made a typo error over here. This is anyways greater than or we know that inner product of xn is greater than or equal to 0. So limit n tends to infinity, that value is also greater than or equal to 0. So we can write inner product of x cap is greater than or equal to 0. Next, we are going to take inner product of x cap is equal to 0. So by definition we can write limit n tends to infinity, inner product of x and xn is equal to 0. So inner product of x and xn is nothing but norm of xn the whole square. Okay, so this is substituted as limit n tends to infinity norm of xn the whole square. So which means that inside value should be equal to 0. That is implies limit n tends to infinity norm of xn is equal to 0, from which we can write x cap is equal to 0. And the reverse part is also true. That is, if x cap is equal to 0, we can write limit n tends to infinity norm xn is equal to 0, which implies limit n tends to infinity norm xn the whole square is equal to 0, which implies limit n tends to infinity inner product of x and xn is equal to 0, which implies inner product of x cap is equal to 0. That is, the if and only if condition is also satisfied. Okay, so all the four properties of inner product are satisfied here in this x cap. The definition that we have taken with respect to the inner product. So inner product of x cap y cap is equal to limit n tends to infinity inner product of x and yn is also an inner product. Okay, so we have proved that it's a vector space, and we have also proved that the definition is an inner product. Okay, next, by using the older theorem 2.3.2, we can already write there exists an isometry A from X to W, which is a subset of H, which is an isometry which preserves the norm. But in our case, we have to prove that A preserves the inner product as well, because we are dealing with the Hilbert space, which is a complete inner product space. Okay, so along with the norm that we have got as part of 2.3.2 older theorem, we also have to prove that A preserves the inner product. So preserving the inner product in the sense, we have to prove that inner product of ax ay is equal to inner product of xy for all x and y element of capital X, and ax ay belongs to capital W. That is, inner product of x cap y cap is equal to inner product of xy, which is needs to be proved. Okay, so let's consider the real part of inner product of x cap y cap. Real part of inner product x cap y cap can be written as real product of, let's substitute the definition that we have already given for this inner product of x cap y cap. It is written as limit n tends to infinity inner product of x and yn. Okay, so if you apply this real part inside, what do we get? We can write it as limit n tends to infinity real part of inner product of x and yn. We know that real part of inner product x and yn is equal to 1 by 4 times norm of xn plus yn square minus norm of xn minus yn the whole square by polarization identity, which we have already studied earlier. Okay, so 1 by 4 is actually a constant. It can be taken outside, and if you apply limit inside for both of these terms, we will get 1 by 4 into limit n tends to infinity norm of xn plus yn the whole square minus limit n tends to infinity norm of xn minus yn the whole square, which is equal to 1 by 4 into, this part is nothing but norm of x plus y the whole square. Okay, and this part is nothing but norm of x minus y the whole square, so which is equal to real part of inner product of x comma y. So we have got that real part of inner product of x cap y cap is equal to real part of inner product of x comma y. Next we have to prove the imaginary part also similar way. Next, imaginary part of inner product of x cap y cap is equal to imaginary part of limit n tends to infinity inner product of x and y n. So applying the imaginary part inside, we can write it as limit n tends to infinity imaginary part of inner product of x and y n, which is equal to 1 by 4 into limit n tends to infinity. We're going to just substitute the value that we have already studied as part of polarization identity for imaginary part of inner product of x and y n, which is equal to 1 by 4 limit n tends to infinity norm of xn plus I y n square minus norm of xn minus I y n square. Okay, so if you apply this limit inside, then we can write it as norm of x plus I y the whole square minus x minus I y the whole square. Okay, so by polarization identity we can write that this is equal to imaginary part of inner product of x comma y. So what we have got is imaginary part of inner product of x cap y cap is equal to imaginary part of inner product of xy. So we have got real part also matches, imaginary part also matches. Okay, so now inner product of x cap y cap is equal to real part of inner product of x cap y cap plus imaginary part of inner product of x cap y cap, which is nothing but which is equivalent to real part of inner product of xy plus imaginary part of xy. So real part of some complex number plus imaginary part of a complex number is nothing but the complex number. Okay, which is equal to inner product of xy. So we have got inner product of x cap y cap is equal to inner product of xy, which is what we had to prove earlier. Okay, so from which we can write that inner product of ax ay is equal to inner product of xy. So we can say that A preserves the inner product space as well. Okay, so we have proved that H is a Hilbert space and A from X to W subset of H is an isomorphism where W is dense in H, and also by theorem 2.3.2 the space H or X cap is unique except for isomorphisms. So hence the theorem. Thank you.